Okay, we're going to wrap up chapter 3. Not much left there. We pretty much finished it last time. We're going to roll into chapter 10, which is energy. Now, as I put an announcement out yesterday, we are going to have a quiz on Monday on chapter 2, and we will take it at the very beginning of lecture. It will cover just chapter 2, so that's pretty much significant figures, conversion, density, that type of stuff. A reminder that you are responsible for the formulas, and that does include the temperature conversions. Those won't be provided for you, so you do need to know those. Any type of maybe some conversions will be provided for you, you know, like maybe a pound, 453.6 grams or something like that. So those will be provided for you, but you know, something like density is mass over volume obviously will not be provided for you. And again, those kind of formulas to convert between the different temperature scales. So we'll take it at the very beginning of lecture. Probably only be 3 or 4 maybe questions, and then obviously we'll continue lecturing afterwards and then off to lab and all that good stuff. Any questions on any of that there? All right. Last time here in chapter 3, we talked about really matter. We talked about 3 different states of matter. We talked about solid, where typically speaking in the solid state of matter, everything is pretty much packed in there pretty tight to one another. It's usually very dense. Usually things in the solid state are rigid and very hard to change the shape. We also talked about the liquid state where typically speaking, there's still atoms, molecules, still really packed in fairly tight to one another, but there definitely is a little bit more room for movement. They're able to sort of pass each other, which is why we see really liquids obviously being fluid, right? And those sort of properties. Liquids don't have a definite shape, but they do have a definite volume. So as we talked about, again, it could go into very much any shape you put the liquid in. But again, if you have, say, 10 milliliters of water, like we talked about last time, if you moved it from different containers, you should still have hopefully 10 milliliters of water if you don't spill it or anything like that. Gas, on the other hand, pretty much at that point, everybody is broken apart from one another. They're flying around the container sort of uniformly. And that causes the pressure that we associate with gases. Yes, sir. Yes, liquids are very fluid. Gases are moving around in the container. We also talked about the different transitions as we go from different phases. Again, if we go from solid to liquid, that is process of melting. Liquid back to solid is freezing. Liquid to gas is evaporation or vaporization. Gas back to liquid, condensation. Then we had our sublimation that obviously went from solid to gas, skipping the liquid phase, and deposition going from gas back to solid, skipping the liquid phase. We got into a little bit about elements. They were obviously the basic blocks, right, of everything. They're as far back as you could go. The basic units of elements are atoms, which, as we'll talk about in a later chapter, obviously contains protons, electrons, and neutrons. Remember, though, that there is a definition that's known as a molecule, and a reminder that a molecule is really just a basic when 2 or more atoms come together, and they could be 2 atoms that are the same element. They could be 2 atoms or more that are different elements. But a molecule is really sort of, you can think about it like a basic definition. I have 2 or more atoms. Again, could be the same, could be different things together. And that's different than a compound like we talked about. A compound does need to contain 2 different elements. So you do need to have 2 different elements or atoms of 2 different elements. You could have more, obviously, but you got to have at least 2 different elements there. So that's why what we talked about, something like water, which is H2O, is a compound. It also meets the definition of a molecule, but it's not an element because it has 2 different elements involved. While something like H2 is a diatomic molecule because there's 2 atoms, but it is still an element because the only atoms there are the same element, which are hydrogen. So again, that's the difference between those 2. We finished up, I think, talking about pure substances. Pure substances are pretty much anything that you have that's sort of by itself, not really mixed with anything. So like we did in lab as well, You know, if you have water, that is a pure substance by itself. If you have salt by itself, that's a pure substance. Obviously, like we did in the lab, when you put them together, we make a mixture. And when we make a mixture, that's basically the combination of two or more pure substances that when they do come together, they still retain their identity, as we could have saw if we had gas last time, but they still retain their identity even though they're mixed together. There's really two types of mixtures. There's a homogeneous mixture where everything looks the same throughout. So after sufficient mixing, typically things will kind of mix together. If you have fluid, it will dissolve perhaps in the liquid part. It will just look like one phase. And that's no matter how much mixing you do, you're still going to really see different phases throughout. Like again, the sand in the water, you can mix that all day. You'll still see the sand obviously in the water. And that's obviously a heterogeneous mixture as opposed to the salt that you put in the water. The salt, if you mixed it enough, it would dissolve and you just look at it and it would just look like water. Any questions on any of that there? We also finished up, and like we were doing in the lab, no matter what type of mixture it is, basically you could do some type of physical means to the components of it. So for example, like we did in lab, you filtered out the sand, and obviously the sand ended up on the filter paper, and it dry out like regular sand it started it with, and the liquid part of the water went through, which obviously is your two components. We didn't get to that part, but again, you were going to take the salt water, would have put it up on the evaporating dish and heated it. That would have released the water in form of steam, which if we wanted to, we really could have collected and got our water back in its original form. And obviously we would have been left with just the salt in your evaporating dish when it was all said and done. And again, so it's, you know, when you make a mixture, it's really physical changes that are sort of happening. There's nothing that's really changed. Everybody's still there in their original sort of form, even though it may not appear that way. You know, making salt water is sort of a physical type change. And that was the last thing that we also talked about in this chapter, which was physical change and chemical changes, which we're going to do labs the next couple of times on those things. Physical change, the really important thing about a physical change is what you start with and what you end up with is fundamentally still the same thing. Nothing has really reacted, nothing has really changed. Maybe an appearance of it has changed, but through some type of physical means, you're able to get back your original sort of substance. And that's different than a chemical change, which usually involves a chemical reaction. What you start with and what you end up with, they're two fundamentally different things. You can't get back your original stuff by any type of physical means. Again, we had something like rust that was formed, which is iron and oxygen that came together. You could throw that rust in the freezer, warm it up and all that good stuff. You will not get the iron metal back. You won't get the oxygen gas back. It has physically changed into something different. Any questions on any of that stuff? Okay. So I think we just had a couple of slides left, I think, here. Just to finish up this chapter. So as we talked about last time, and as you pretty much did in lab, there are two really good ways to separate out mixtures. Filtration, as we did sort of in lab, and as you saw, is a really good way to sort of separate out a solid from a liquid. Obviously using our filter paper up here, like you did when you pour it through here, liquid part goes through, basically the solid part stays on the filter paper, and a very, very easy, convenient way to separate out that mixture. And again, you could take whatever is here and you obviously can dry it out or whatever it may be, and a very, very good way to do that. Distillation is a more sort of advanced method, if you will. Really the same principle of what we were going to do in lab, where we were going to heat it up on the evaporating dish. And I think I drew it last time, but let's take a look at a much better picture I'm assuming here. This is really a distillation apparatus, and it's really a closed environment here. And it's basically two flasks, for example, kind of connected by a tube. And as we talked about, basically that tube is usually kept very, very cold. And by heating something like salt water here, which is a homogeneous mixture, what we're able to do is take advantage really of the differences in physical properties of the two substances. We basically have salt, which is an ionic compound. Ionic compounds are held together extremely, extremely strong. They have super, super high boiling points. They typically don't boil under normal conditions. And we have water, which will boil at 100 degrees Celsius. So by taking advantage of those differences in their sort of physical properties and heating it up, we could get the water part of the mixture basically to start to evaporate. And as we talked about, when it starts to evaporate, it's going to make steam, which obviously has nowhere to go but through the tube here. And once that sort of steam, which is really the gas version of water, hits the cold, it's going to go through condensation. And that's going to allow, as you can see on this side, basically the water part to drip off and be separated out. So even though salt water, you look at it, it all just looks like water, like I don't see the salt anywhere, you know, you're able to use this technique to really separate it out. Obviously, if we continue that process, and if you would have continued that process in your evaporating dish, you would have been left with basically a pile of salt at the end. And obviously, we just now have separated out, like we talked about, our two components of our mixture, both in their original forms. Neither one really transformed into anything different from where it started with. And again, this is more of a physical change that's sort of occurring here. Any questions on that there? My bad drawing last time looks sort of like that if you close your eyes, I think. So I think that is it for this chapter. Any questions on chapter 3 there? Yeah. Yeah, distillation is really a method. It's a method like filtration. So there's not necessarily a definition for it, but it's a technique that you can use really to exploit differences in boiling points. Like here, we're exploiting really waters boiling much, much sooner than the salt would ever boil and being able to separate it out. So not necessarily a definition, but it's more of a technique that's used. Yeah. Other questions? Okay, just give me a sec here to queue up chapter 10 and we'll get chapter 10 here. And chapter 10 is about energy. So we're going to skip ahead a few chapters and then we'll obviously come back to all the ones we just skipped. So let's talk a little bit about energy. When we talk about energy, it oftentimes involves what is sometimes referred to as sort of thermodynamics. Thermodynamics and chemistry deals with a lot of things, energy being one of them. And it deals really with the idea of a lot of times later on, if you continue on to take 1B, for example, it deals with ideas of whether or not a reaction will occur under normal conditions or certain conditions. Will they occur spontaneously? So one important thing to remember as you go through sort of chemistry, when we talk about something being spontaneous, it doesn't really have to do anything with how fast or slow it occurs. When we talk about in terms of thermodynamics, something being spontaneous, what we're really referring to is under certain conditions, will this reaction occur? And it could occur really fast, it could occur really slow. It just means that, you know, it will basically occur. So oftentimes we deal with two different parts. We deal with the system, and the system really is any part of the universe that we're interested in. So if we're doing some type of, you know, experiment in a beaker, the beaker's our system, and that leaves pretty much everything outside of that as the surroundings. And a lot of times when we talk about energy, we talk about really this sort of flow of energy from perhaps the system to the surroundings or vice versa. So, you know, if we have a system and then obviously the surroundings, we really look at sort of the flow of energy either into the system or out of the system. And depending on sort of which way it is flowing, you know, we'll talk about what it sort of means, whether or not, for example, it's exothermic reaction happening or an endothermic reaction. We do deal with three types of systems typically. An open system, which is oftentimes what we deal with, for example, in lab, it's open, which means we could exchange mass. We could also exchange energy with the surroundings. There's also a closed system, which we see the transfer of energy, but really not mass. And there's really an isolated system, which is pretty much incubated from everything, no energy being transferred, really no mass being able to be taken in and out. So, if we think about like there's an open beaker, pretty open system, energy could kind of flow in and out. We could also reach into our beaker or pour stuff out, obviously, of our beaker. It's open, so in a lot of cases, we do deal with sort of open systems a lot of times when we are doing experiments. And here's an example that obviously, again, we could have that exchange of the matter that's in there, the mass, and obviously the heat exchange that's occurring in that open system. You can very much create a closed system by simply, for example, throwing a stopper up there on top of your flask. Obviously, that's going to prevent any mass from leaving. And we still have, though, the exchange of energy or heat going in and out. And obviously, an isolated system is pretty much kind of locked in there. And, we're not going to get exchange happening of a lot of things. So most of the time we're hanging out in an open system. Sometimes we do put sort of a lid on things and we have sort of a closed system in terms of that. But most of the time here we kind of deal with open type systems. So let's talk a little about energy and some of the definitions and some different types of energy that we come across. So energy is really the capacity to do some type of work or produce change. Energy is basically equal to work done, which a lot of times equates to force times distance. There is a lot of sort of different types of energy that we do come across. There is chemical energy, which, for example, is stored within the actual molecules itself. There's actually a lot of exchange, for example, of energy when we make bonds or break bonds, for example. So, for example, if we had a bond and we wanted to break it, would we have to put energy in or take energy out to do that, you think? We would actually need to put energy in to do that. And basically what happens if we have a bond, we put energy in, everybody gains energy, they wiggle away from each other, not really like that, but they sort of wiggle away, they gain enough energy. They're able really to break apart from one another. Opposite of that is if we want to kind of make a bond, it actually requires energy to be basically released or put out by each of those guys. If you think about it, we got two things kind of vibrating a lot. As they lose energy, they sort of slow down and they're able really to kind of come together and make that bond. And two words that we will see a number of times as we go through here. Whenever we sort of absorb energy, that is what is known as an endothermic process, as we'll see a lot of in this lecture here. And anything where we sort of energy is out or released, it's usually how it's described, that is what is referred to as a exothermic type of process. Now, there's other sort of energy, obviously, that we come across. Potential energy, for example. Potential energy is stored energy, sometimes referred to as basically the energy associated with the position of an object. The classic example in most books is the big giant boulder on the very top of the hill that's about ready to fall off. It has a certain amount of energy based on its location. And then it can be transformed into other types of energy, like kinetic energy. So if the boulder comes over the hill and starts rolling down the hill, that potential energy will be converted into kinetic energy until it splats on the bottom. Hopefully nobody's underneath there. And it will then come to a rest with new potential energy. There is the idea, though, of really the law of conservation of energy, which is sometimes referred to also as the first law of thermodynamics. The idea here is energy cannot be created nor destroyed. It can be transferred from one version to the next or from one spot to the next, and that's very common as well. For example, the boulder example. We have the boulder up here. It has a certain amount of energy. As it transfers down, it goes to kinetic energy. When it hits, say, the ground, it transfers that energy to the ground. So we got this kind of complete transfer of energy. So one thing that we sort of see a lot as we talk about energy is this idea of sort of a perfect transfer of energy from, say, the system to the surroundings, or vice versa. So basically, what we end up seeing is if something loses a certain amount of energy. So let's just say, for example, something loses 100 kilojoules of energy, it just gives it off. There has to be something else that will basically absorb or take in that 100 kilojoules of energy. So there's sort of this nice perfect transfer of energy from one place to the next. You know, we don't lose it. For example, if you had something that was really hot, right, and it's giving off energy, you touch it, your hand hurts and you burn yourself, which you should not do. But all that energy is now transferred to your hand, right? So what energy would be given off would be transferred to your hand. Don't recommend that, especially today, right? As we're in lab, we're heating things up. Don't do that. But there is this sort of transfer that occurs, even an ice cube, right? So ice cube just sitting there, the surrounding is giving off heat, right? The ice cube's accepting the heat, the ice cube starts to melt. So there's this nice transfer of energy that we typically do see. So thermodynamics, as I talked about, really is the study of things like energy. And as you continue through your chemistry career here, you'll learn about some other things. But it really does deal with the idea, for our purposes here in this class, of heat and energy and sort of what happens as they convert it. One really important sort of aspect of things like energy is it is referred to as what is referred to as a state function. And state functions are really properties that do not basically are determined by sort of how you got there. There's really sort of only two really important things when we think about state functions, and that sort of is where you started and where you ended up. So the idea here is, for example, we have two different hikers. Hiker blue took really the kind of straight path to the top of the mountain there. Hiker in the red kind of took the scenic route around the mountain. What they end up with in terms of potential energy is they actually end up in the same potential energy because they're both at the same basically point. Where they started, where they ended, is basically the exact same spots, and they have basically the exact same potential energy. Now, that's really important in chemistry. Oftentimes people have the misconception that, you know, all reactions sort of occur in like a one-step deal. It's like boom to boom and it's done. And that's not really the case. There are lots and lots of reactions that it takes many individual steps or reactions to kind of get you to the end product. And because something like energy is a state function, you could add up all those steps and they all should end up in the same sort of spot. That's why a lot of things we look at are calculated by sort of final state and initial state when we look at things. And that's what these things are here. This is the change in internal energy, and that little delta means change, the little triangle. And that is basically the final energy minus the initial energy. This is change in pressure, final minus initial, change in volume, final minus initial, and change in temperature being final minus initial. So a lot of things that we sort of calculate, and especially with terms of energy, is looking at, you know, where we started in terms of conditions and basically where we ended. And that's how we can sort of figure it out. When we think about a chemical reaction that occurs, like a chemical change, and again, this is where jumping to chapter 10, maybe it's not so good. But when we look at a reaction or an equation, there's an arrow, and on the left-hand side of the arrow, those are what are referred to as reactants. Those are our starting material. So our reactants are our starting material in a chemical reaction. On the right-hand side are what are known as our products, and those are what are formed as a result of a chemical reaction. And if you think about a reaction, that's also like final and initial. Initial would be our reactants, final would be our products. So a lot of times when we calculate something like energy, one form of energy that we oftentimes calculate what is known as delta H. That is what is known as the enthalpy. It's basically the heat of a reaction. And one of the ways that you could calculate the delta H for a reaction is to basically calculate the delta H of a reaction is equal to the delta H of your products minus the delta H of your reactants. So we take basically our final, which is our products, minus our initial, and that is how we can calculate something like delta H, which is a very common sort of value that we use to figure out for a particular reaction. Is this reaction exothermic? Is it giving off energy? Is this reaction endothermic, sort of absorbing energy? So a lot of times in reactions, we think of it as final and initial, products minus reactants, sort of where we ended up versus where we started. And that's a very common way that we sort of figure out things like energy in reactions. Any questions on that there? Yes. What letters there? Yeah, this is a reaction. I'm sorry, that's a reaction. There. Okay. Is it shorthand for reaction? Yep. Question? Oh, yeah. It sort of represents, if you look at a reaction, we'll talk a little bit about it in the chapter. We don't go super deep into enthalpy. When you take 1A, you'll go really into a lot more. But you could think of it as sort of the overall sort of energy of a reaction, whether or not, for example, when you look at a reaction, would you expect that reaction to sort of overall absorb energy, or will it sort of give off energy? So for example, when you light a Bunsen burner, for example, that is a flame that's giving off heat and energy. That's an exothermic reaction. And that reaction of basically methane, which is the gas coming out, and oxygen overall produces energy and giving off heat and stuff like that. You know, as opposed to, for example, if you ever had a cold pack where you break it, it does a reaction, feels really cold, right? You know, that reaction is absorbing energy, which is why it feels cold in your hand or something like that. Yeah, so it's just a matter of, as we'll see a little bit, it's just a matter of looking at a particular reaction and just that reaction itself, you know, is it going to sort of give off the energy or absorb the energy? To look at where that energy went, you have to do some other calculations and stuff like that. Other questions? In most cases, there is usually some exchange of energy, if that's sort of what you're talking about. You know, there's different degrees like anything else. There's certain things that give off a lot of energy, for example. There's certain reactions that give off just like, you know, barely measured sort of energy. So there's usually, you know, associated with I would say most reactions or something like that, there's some degree of energy transfer, either it's going to be given off or absorbed. And again, it can be different degrees of lots or very, very, very small, almost like none being given off. So very rarely you probably hit something that is like perfectly zero, in terms of absorbing or stuff like that. Yeah. So let's talk a little bit about energy and some of the important units associated with energy. Energy is, the SI units is Newton meters, which we never use. But sometimes you do see the other set of units there, which are kilograms meters squared over second squared. But more often, the most common sort of units of energy that we come across are joules. So 1 joule, and that's not negative, that's just from PowerPoint, but 1 joule is equal to 1 kilogram times meter squared second squared. Although personally in this class, we don't get too much. That conversion does come across a lot in chemistry as you continue on. Kilograms meter squared over second squared is equal to a joule. Kilojoules is another very common way that we basically express energy. So 1 kilojoule, 1,000 joules. Again, none of these are negatives, just from PowerPoint. The other sort of units that we come across are calories. A calorie, which is a lowercase c, is basically the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. And there's an important relationship between calories and joules. 1 calorie is 4.184 joules. So this conversion here, we do use a lot, especially later on here when we get into some specific heat. So we'll see this conversion a lot. Obviously, 1,000 joules to a kilojoule is something that we do use a lot in this class. Not a heck of a lot in this class, this relationship, but you will see it later on if you continue to take chemistry classes. There is another sort of calorie that's sometimes used for energy, and that is a capital calorie. A capital calorie there with a capital C. That is really a nutritional calorie. And one of the calories with a capital C is actually equal to 1,000 of the little calories, the little c, and that is also equal to 1 kilocalorie. So 1 kilocalorie, which is another conversion we come across a lot, is equal to 1,000 of the little calories or little c's. So nutritional calories obviously is like on our food. If you're at the gym or running on a treadmill, right? Sometimes we'll tell you how many calories you burned, or old treadmills used to tell you how many kilocalories you burned, which is the same thing as a nutritional calorie. And so those are common units that we see. Again, in chemistry, these 4 units are really common in terms of energy: kilojoules, joules, little calories, and kilocalories. These are 4 sort of energy units that we do come across a lot in chemistry. And going between joules and calories, we do a lot as well. Any questions on that there? Obviously, one way that we could use energy is to change the temperature of a substance. Obviously, if something is gaining a lot of energy, we would be able to sort of recognize that by watching the temperature of that substance go up, right? So if something absorbs energy, we should be able to sort of recognize that as the temperature increases. If something is sort of given off energy, we should see the temperature actually go the other way. It should start to drop. So if we have a substance that itself is giving away the energy or releasing the energy, we should actually see a drop in the temperature, where the final temperature actually will be less than the initial temperature in that particular situation. Now, thermal energy is a little bit different than temperature. Sometimes people think thermal energy is the same thing as temperature. Thermal energy is really associated with the random motion of molecules. So a lot of thermal energy when you have a lot of molecules. More molecules, more atoms, more chance they're moving around, vibrating, more vibrations and all that kind of stuff, the more thermal energy is really associated with it. Now, there is a distinction, as I said, between really thermal energy and temperature. So, for example, you could have, for example, a coffee cup that has a higher temperature than, say, a bathtub that's full of water. But in terms of thermal energy, the bathtub would have a lot more thermal energy because obviously it contains a lot more molecules, a lot more atoms vibrating around than, say, your coffee cup, which may just have a higher temperature being shown in there. I think is this example. So again, if you had something like that, even though that coffee cup, has a higher temperature, the actual water at a lower temperature would have more thermal energy because, again, of the greater number of molecules that would be present. Coffee cup itself ends up with a higher temperature because there's not so many atoms in there, or molecules, right? Smaller volume, less energy needed to raise the temperature. So it does reflect a higher temperature. More atoms takes a lot more energy to get that temperature to an equivalent temperature. So there is a distinction between temperature and thermal energy. But we do look at temperature really as a measure a lot of times. And it's a very good measure to help us determine, exothermic, endothermic. And as we'll do a lab maybe towards the end of next week, you can simply take a thermometer, stick it in a reaction, and really just by sort of following the temperature change that occurs, you could actually calculate how much energy maybe was absorbed, how much energy was released by a reaction that was taking place by simply just sort of following the temperature. So temperature is a really nice gauge. It's an easy way to sort of help us understand and sort of track, if you will, sort of where the energy is going. So as we've been talking about a little bit about some of these different types of processes, heat can be defined as really the flow of energy due to a temperature distance. Now, heat flows from cold to hot or hot to cold? It goes from hot to cold. So the guy that's hotter releases the energy, the guy that's colder picks up the energy. And if they happen to be an insulated container, they'll meet somewhere in the middle of their temperatures. But typically the flow of energy goes from hot to cold. So as we talked about, there really is two types of processes that we oftentimes look at as we're talking about energy. One is an exothermic process, which really is any process that releases energy. Energy is given off. Obviously, striking a match, lighting a match, a Bunsen burner, you can feel the heat coming off, right? So that is an exothermic type process. Endothermic, on the other hand, is a process where heat and energy is being really absorbed by the system. Now, in terms of calculations, there's kind of two different ways that we sort of represent heat or energy, at least in this class. One very common way that we do is we use, and we'll talk about how to calculate it in just a bit, but we use Q. Q represents the heat of a reaction. And when we calculate something like Q, which we'll learn a little bit later on in this chapter, we will end up with really one of two things. We'll end up with a number that's either positive or a number that is negative. And typically anything that is exothermic will result in a negative sort of value when you actually calculate the heat or energy is associated with something. The other one is our delta H that we talked about a little bit before, which is our enthalpy, which again is sort of that like overall energy associated with a particular chemical reaction occurs. Also, if you calculate delta H, are very common. Sometimes even in a reaction, they'll just give you the equation and go, the delta H value is negative, whatever the number may be. The number is really not important. The actual sign is really important. When you see that negative, it indicates that that reaction is exothermic. So As we go through this chapter and just in chemistry in general, when you calculate things in terms of energy, you end up with a negative value. That should be indicating a exothermic type reaction, that overall energy is being given off. Endothermic is pretty much the opposite of that. They are positive sort of values. So if you calculate Q and you end up with a positive number, that is usually indicative that the reaction is endothermic. And delta H as well, also a positive number will, positive number there will indicate a endothermic process. We will see much better pictures that I'm going to draw, but there are what are sometimes referred to as energy diagrams, just to kind of show this. So that is energy there on the Y, and the reaction is progressing this way. When we look at something that is a exothermic reaction, this energy diagram sort of looks like this, where over here in this flat spot is the reactants. I'll just put R. Over here, or maybe right, there we go. Over here is our products. Did not like that, there we go. And what we do see is our reactants are higher in energy than our products. So the only way for our products to get down to our products is energy needs to be released. And that is a different diagram, as we'll see a much better picture in just a sec, but where we have our reactants and our products. Our reactants are lower in energy than our products. That is an endothermic one. In order to get to our products, overall energy needs to be absorbed by the system as the reaction is occurring. So energy needs to be absorbed. So if you ever see sort of an energy diagram that sort of looks like that, wherever you have reactants, they always start out higher in energy than their products. That always will result in an exothermic reaction, which means energy has to be released to do so. Whenever you have reactants lower in energy than our products, which are higher in energy, energy has to be sort of absorbed and put in there. Any questions on that there? So here's much prettier picture of sort of my drawing there. But on the left here, again, we have our energy of our reactants, which are higher in energy than our products. And that is our exothermic reaction. And on the right, we have our endothermic reaction, where the reactants are starting out lower in energy than our products. Now, there's also another important sort of energy aspect in terms of reactions, and that is the activation energy. The activation energy is sometimes abbreviated E of A, standing for obviously activation energy. And the activation energy is really the hill that the reactants has to climb basically to get to the other side. So what happens as this reaction progresses, we have our reactants. As the reaction starts to go, they need to start breaking their bonds, right? So everybody there, they pretty much has to break apart. By the way, a reaction is basically just the breaking apart of all the bonds on the reactant side, and then everybody reassembles in sort of a new location on the product side. So as a reaction starts, you're starting to break apart the bonds of your reactants, your starting material, but we need to start actually forming some bonds along the way as well. So we get the guys breaking the bonds here, and then we start to form some bonds. And that's really what's happening, for example, as we kind of come up this hill here. So as we're approaching and coming up this hill, we get really the reactants starting to break apart all of their bonds, not completely, they're partially breaking their bonds, but really at the same time, they're actually starting to make their new bonds at the same time. So we get to the very, very top of the hill here in terms of energy. And one thing that you should keep in mind in chemistry, do we think things like to be in really high energy or low energy? Yeah, it's like us. We don't want to be high energy all the time, right? So we want to mellow out. So things really want to be in very, very sort of the lowest energy that they can achieve. So when things are in high energy, they're not very stable. They're very reactive. They want to kind of get out of that position. So when we get to the very peak of this curve, this is what is sometimes referred to as the transition state. In the transition state, we get what is sometimes referred to as the transition state complex, sometimes called the activated complex as well. And basically at the very, very top of this hill, this transition state complex is a substance that has partially made bonds, partially broken bonds, like an intermediate kind of between the reactants and the products. So because it's like the peak of the energy and it's the highest point you can kind of get, it's not going to hang around a very long time. It wants to really drop down the other side relatively quickly to make those products, because again, it's in a state of really high energy and it doesn't want to be there. So usually very quickly, it will kind of drop back down into our products. And that's why a lot of times people have a very difficult time, for example, trying to isolate that kind of transition state complex, that kind of really high energy thing, because it really doesn't stay around very long. It's sort of unstable. We see the same thing here on our endothermic. Again, we're starting to break bonds, starting to make bonds. We get to the very top there, which would be our transition state. And again, it will kind of come off into our products. The transition state and sort of the hill of it, or how big it is, has a really big effect on how fast or slow a reaction occurs. If I have something that has a really small activation energy, would I expect that reaction to be fast or slower than something with a larger activation energy? It should be faster. It has a much smaller hill to climb, like yourself. If you're walking up a really small hill, you should be able to get over to the other side a lot quicker than you had to walk up a giant mountain, right, to get to the other side. It's going to take you a longer period of time. So activation energy, does play an effect on the rate of a reaction. And really, the lower the activation energy, typically the faster it will sort of occur, and obviously vice versa as well. The larger the activation energy, the slower that reaction would occur. Is there a difference that we see in these pictures of the activation energy between exothermic and endothermic? Which one is smaller? It is the exothermic one on the right, or left here. It is much smaller, and it's this area here, which means we would expect this reaction to occur a lot faster. Also means that there's probably a greater proportion of molecules that really do possess enough energy to get up and over to the other side, and that reaction probably will occur relatively good and pretty good. As opposed to here, takes a lot more energy, right, to get everybody up and over to the other side. Is that big giant hill there. Also why perhaps that's an endothermic reaction. It needs to overall sort of gain some energy to help everybody get up and over to the other side. Now, sometimes people think that, all you need for a reaction to really take place is everybody to hit each other. And the truth is, you do need collisions to occur, but you actually need everybody to hit each other in sort of the right location, sort of the active spot for a reaction to take place. You can have a lot of collisions in the wrong spot, nothing will form, no products will form. The second part of that is, as they collide with each other, you also need them to have that minimum amount of energy to really get this reaction to occur, basically enough energy to get themselves up and over that hill to the other side. So if one of those two things are lacking, they don't hit each other in the right spot, the reactants, or they don't hit each other with the right amount of energy, you will not see product form. So even though they come together, may not result in products being formed. Those two things are really, really important in order for products to be formed in a reaction. Any questions on any of that? And here's just another sort of representation of this. This is an exothermic reaction. hydrogen gas, oxygen gas forming water. We can see our product here is water. And as a result, we see our product is lower in energy than our reactants where we started with. So that means energy has to be given off. As we were talking about sort of that conservation of energy, as we do this, for example, the air, the surroundings would be the one that would pick up all that sort of excess energy that would be given off in this reaction. On the other side, we actually have a decomposition reaction, mercury 2 oxide, and it's going to form mercury liquid and some oxygen gas. We see the mercury 2 oxide, which is on the bottom, the HGO. That is lower in energy than our product in this case, which is the mercury and the oxygen gas up there on top. Energy needs to be absorbed for this reaction to take place. So, just a basic example, the ice cube is really an endothermic process for the ice cube. It sits out, even if you don't supply extra energy, it's going to pick up all that energy from the surroundings and again, start to melt. If you take the liquid water to get it to steam, you do need to do that. A little bit of heat will allow that to happen. And those are all endothermic processes. So as we talked about, I think the other day when we were talking about sort of matter and the different states of matter, when we talk about endothermic, that's as we go from like solid to liquid to gas, right? Those are all endothermic processes. We need to put energy in to do that. Exothermic, going the opposite way, gas to liquid, as we talked about the other day, to solid. So even something as simple as changing the phase of something requires either energy in or energy out to sort of do those processes. Any questions on that? Now, we sometimes will look at energy in a chemical equation, and we could get some information as to whether or not this reaction, again, would be exothermic or endothermic. Again, a reminder, when we look at a chemical equation, which is what represents a chemical reaction, it's always this situation here, our reactants to our products. So if we look at the exothermic reaction, this is actually what happens when you light a Bunsen burner. A little bit of methane, some oxygen from the air, a little bit of a spark, and you get fire. It's an exothermic reaction, and we see 213 kilocalories released. But more importantly, when we look at an equation, sometimes people will write the actual energy into the equation. Not very often, but sometimes you may see it. But important though, if you do see it written into the equation, it will typically always be on the product side. So if you see some type of energy value actually written into the equation, and it's an exothermic reaction, it should be on the product side or the right-hand side of the arrow. And that is opposite than our endothermic. We see the energy written on the left-hand side or the reactant side of the reaction or the arrow, and that indicates a endothermic reaction. Again, in most cases that you'll come across probably reactions is they won't write it in. They will use that delta H value as we talked about earlier. And that delta H value again would be negative for exothermic and positive for endothermic. And usually, for example, they'll just write H2 plus I2, 2HI, and they'll go, hey, the delta H is 12 kilocalories. And that's usually how it'll sort of be written. There'll just be this separate distinction, which is a very common way of doing it. Again, Q as well, which is heat. We will calculate Q a lot in this class. And again, that negative positive thing goes for that as well. So exothermic heat released, if we see it in an equation, we could think of it, we could think of heat and energy as a product. And for endothermic, heat is absorbed. And again, if we see heat and energy in a reaction, we could think of it as acting like a reactant. The very last chapter we'll talk about in this class You know, that's an important aspect to keep in mind, energy as either a reactant or product. When we talk about something like Le Chatelier's principle at the very, very end of this semester, you know, we kind of see that aspect of it, thinking of it as a reactant or product. Any questions on that? So again, if we have, this would be a more isolated sort of container here. And obviously our hot water here, as we talked about, heat always flows from hot to cold. So basically the hot water is being exothermic, if you will. The cold water is being endothermic. We see the hot water will start to cool down. The cold water there will start to warm up. And eventually they will meet somewhere there in the middle as they're bouncing around. And you can see they meet somewhere in the middle on both sides. Again, definitely in this sort of insulated container. It's not going to be affected by any heat or energy from the outside or surroundings, right? So it's going to keep everything basically isolated in there. As we'll also see when we do the experiment, I think next week, you know, you could almost do this with something as simple as like styrofoam coffee cups. They work really well, and that's what we'll use. You could use styrofoam coffee cups to really insulate, you know, for example, water inside, and that allows you really to determine what is happening with the water. Is it gaining energy or losing energy by watching the thermometer and the temperature change? And it has really no extra influence from outside of the actual system that you're dealing with. So as I mentioned before, and a little bit before, we do oftentimes in chemistry come across enthalpy. Oops, sorry, I want to get back here. If I get back there, there we go. Maybe there it is. So most reactions are carried out at constant pressure. So if we were to do something inside the lab, obviously the pressure of the room is not changing all that much. And enthalpy, which is delta H, is oftentimes used, as I mentioned before, to express, you know, whether the heat is being released or absorbed during reactions. And oftentimes in a reaction or equation, you're given the overall delta H value, which is that little triangle H for a reaction. A very common way, as I mentioned earlier, that we calculate these things is we can basically take everything on the product side, add up all the delta H values. Where would you get the delta H values? There's actually a big giant table of delta H values for all kinds of molecules and stuff. You could look up the values for all the guys on the product side. And basically you would add up all the energy that the product has. And basically you would subtract it from all the delta H values from the reactant side. Again, also a table, you could go and look up the values for all those guys. And this comes back to what we were talking about earlier. Basically, products minus reactants, final state minus initial state. Again, the idea of really the two important things is where you start and where you end in terms of energy. And that's oftentimes how we calculate something like delta H. And as we talked about a number of times up to this point, positive value endothermic, negative value exothermic. For our purposes, the actual number is not that important. It's really just the sign. So negative or positive tells you it's exothermic or endothermic. Also why, as we go through some of these calculations, it's really important to do the calculations sort of correctly. It's really the temperature part. And it's important to do that because you want to make sure you do the calculation correctly to end up with either a negative value or a positive value. So the idea behind that is the temperature part of it. You just figure out whatever the difference in temperature is, say 5 degrees, right? Always going to give you a positive number no matter what happened. Now, if you started at 0 and ended at 5 degrees, 5 minus 0 is positive 5. If you started at 0 and ended at negative 5, you're going to end up with the same 5 degrees difference. So it's really important always to end up taking, when we do change in temperature, as we'll talk about, you always want to do final minus initial, because that's really what's going to give you that sort of positive or negative value in your energy answer and going to allow you to figure out whether it's exothermic or endothermic. Sometimes people are taught when we do an equation like we're going to see in just a second, you know, just take the difference in temperature, regardless of sign, just, you know, take the difference. And you'll get the same answer. Numerically, you'll get the same answer, but you really won't get the important part of that answer, which is whether or not it's positive or negative. And that's really important, especially in chemistry, to allow you to understand whether or not you're dealing with exothermic or endothermic processes. So let's take a look at that equation I'm talking about. So a very common way we deal with heat and energy in this class is we calculate something which is referred to as specific heat. And the specific heat capacity of a substance is the amount of energy that's required to change the temperature of 1 gram of a substance by 1 degree Celsius. It's pretty much the identical definition of a calorie, except that a calorie is 1 gram of water per 1 degree Celsius. There is a specific heat equation that we use, and it's the one in the box, and you do need to know it, obviously. And it is Q is equal to ms delta T. Q is heat or energy. And it typically has units of joules or calories. So joules or calories are the typical units that we use to calculate Q. And that is the Q that I've been talking about that could be positive if it's endothermic or negative if it's exothermic. M is mass, and it is in units of grams. S is the specific heat capacity. And it has units of joules per gram per degree Celsius or calories per gram per degree Celsius. And that is really the definition of specific heat capacity. Joules energy, so it's the energy required to change 1 gram on the bottom per 1 degree Celsius. Now, most important here is what I was just talking about, and that is actually our delta T. You always want to do delta T as our final temperature minus our initial temperature. And you always want to do that because when we look at this equation, S is a positive number, always. M is a positive number. So really the only place we're going to get our negative value for Q is that change in temperature. So it's definitely not where you just want to take the difference in the temperature. You want to make sure that you always do final minus initial. That's where you're going to get that negative value or positive value for Q. Important couple of values: specific heat of liquid water, again, not negative, that's just from PowerPoint, is 4.184 joules per gram per degree Celsius, or 1 calorie per gram per degree Celsius is the specific heat of liquid water. So these two numbers definitely we come across a lot or use a lot. A lot of times we use the joules, but calories are used a lot as well. And again, this is really for liquid water. I say that because, for example, the specific heat capacity for ice, which is water in its solid form, is like 2 joules per gram per degree Celsius. And for steam, it's like 2.03 joules per gram per degree Celsius. So the state of the substance does matter when you look up something like the specific heat capacity. But a lot of times when we do reactions or experiments, like I was talking about earlier, just simply taking a styrofoam cup, put some water in it or something like that, we use the specific heat capacity of liquid water, which is 4.184. We use it a lot in calculations. Most of the times when we take a solution, it is aqueous. You'll sometimes see this symbol next to it, AQ. That is aqueous. Aqueous is a solution, is different than a pure liquid. Water by itself, H2O, is a pure liquid, gets the little L symbol, if you will. Something like salt water, like we made the other day, that would get an AQ symbol next to it, aqueous. Typically, something that is aqueous is made by taking something like water and dissolving something in it, like salt, and you make salt water. Now, typically, since most aqueous things are water-based, we could do a lot of reactions and just use the specific heat capacity of water, which is the main component of those solutions, to help us calculate the heat and energy going through. You could do a simple reaction where, like we'll do next week, with a thermometer, following the temperature change, getting the mass, you could calculate how much energy was released in the reaction or absorbed in a particular reaction. Any questions on that there? Here are some specific heat capacities of some different substances. And again, you can see these are all really water, but they do have some different values depending on the sort of state it's in. And again, though, we do use really that liquid one the most. And then obviously some other things. If something has a large specific heat capacity, would it take more energy or less energy to change the temperature by 1 degree of something that has a smaller specific heat capacity? The larger the specific heat capacity, the more energy is needed to change it by 1 degree Celsius, right? So the larger the specific heat capacity, the more energy you would have to put in there to make the temperature change by 1 degree Celsius. So for example, gold, you would only need to put in there 0.13 joules per gram to get it to move basically 1 degree Celsius. Something like liquid water, you need to put in there 4.184 joules, right? A lot more energy to do that. That is why people get upset when the water temperature goes up by a very small amount, right? Like the ocean, because that's water. It takes a lot of energy to make water change its temperature by 1 degree Celsius. So even you go like, it's only like a half a degree. It took a heck of a lot of energy to make that half a degree temperature rise, right? So something that has a larger specific heat capacity will take a lot more energy to get that temperature change to occur than something that obviously has a smaller specific heat capacity. All right, so let's finish up here with one example. Let's see what you come up with. So take a minute or two, determine the amount of energy that's required to raise the temperature of a 10-gram sample of aluminum, specific heat capacity 8.89, from 25 to 58. So take a second or a minute or so and specific heat. So we want to use our formula of Q is equal to MS delta T. By the way, I use S. Sometimes some books will use C instead of S for specific heat. Some books might use SH as well. So most books will use S, but some books will use maybe like a C sometimes to represent specific heat capacity. If we just pull out the information, obviously our mass here is 10 grams. We have our specific heat capacity, which is 0.89 joules per gram per degree Celsius. Our initial temperature is 25 degrees Celsius, and our final temperature is 58 degrees Celsius. So we really have everything we need to plug into here. So our Q would equal our 10 grams times our specific heat capacity, 0.89 joules per gram per degree Celsius. Now, again, here we want to go final minus initial. So that's going to be 58 minus 25 degrees Celsius. In terms of units, grams cancel, degrees Celsius cancels. We're left with joules, which is all left over, which is a unit of energy, which is good. And it looks like a 293.7 on your calculator. Now, let's talk about Sig Figs. This guy has 3. This guy has 2. When we do the subtraction here, we end up with 2 as well, Sig Figs, which means really this should be 2 Sig Figs, or like 290 joules. First off, any questions on the calculation? Is this reaction endothermic or exothermic? Yes, sir. It is endothermic. Our Q value here is positive. So overall, this reaction is going to absorb the energy. We know that's true because we actually see the temperature go up, right? So the only way the temperature could go up, it has to absorb energy to require the temperature to raise. Any questions on that there? All right, we will lay it up here.